Good morning, everyone. So today I will give a talk. I will show, I will give an introduction to the energy dispersive spectrum. I mean, EDS and the electron energy loss spectrum use. So as you know, these two techniques can be done with, attached with our TEM. So this tool is a very powerful thing to analyze the chemical composition and also the valence state of the element of the elements. So as you know, for EDS and use, there are so many things to cover. But today, I would like to introduce some critical point. I will cover the principle of EDS and use, and also some key point parameter for EDS use, and also some application. The next step in the future, I will cover the quantification of the EDS and use. So why here I included some key parameter, because for the use analyze, you need to be familiar, with the parameter you use during the experiment. This is very important for your quantification. The thing is, most people will take the EDS and use. Then when they go back, they forget everything. They didn't know the parameter they use. And also, acquire the good data is the first thing for your quantification. So that's why usually before you do the TM, before you do the EDS and use, you need to think what is your purpose, and you need to think which parameter is the best one you can choose for your experiment. And also you need to be familiar with any artifact related to your technique. So I will cover this in the following. So I believe you see this figure many times. So this figure shows the interaction between your sample and the electron beam. So the electron beam, when the electron beam penetrates through your sample, for our TM, as you know, it's very thin. So the electron beam can pass through the whole sample. So if you the signal for the transmitted electrons, we can use it for imaging, and we can also so for some elastic scattering, we use this electron for diffraction under HRTM. We also contain some inelastic scattering. This is usually used for use and study for image. So what is the EDS signal? The EDS come from here. So you can see this area, the EDS coming from here. You can see the volume of your the volume between your sample and the electron beam. That means this is a very large area. So that's why usually the spatial resolution for EDS is not so good. And also you have this continuous X-ray. Basically today I will cover X-ray like here and use like here. Okay. And there are some other signals like the secondary electron you can use for SEM, and also the backscattered electron you can use BSE the detector. So there's some auger electron. I mean, there are many signals you can use. So the first thing, I will cover something about the X-ray emission. So as you know, most people will tell you the EDS is not the best way to analyze the light element like lithium, boron, but why? What's the reason? So you need to understand this. The X-ray usually is when the electron interacts with your sample, your atom will be ionized. So the ionized, for example, the ionized atom does not sometimes they lose the energy by giving over the characteristic X-ray. That means they cannot only give over characteristic X-ray, but also emit an Auger electron. So there are two possibilities. Thus, I mean, we have the Florence yield describe the probabilities of the X-ray versus the Auger emission. Now you can use this formula to show to calculate the Florence yield. So you can see when the atomic number is larger, this one, this is the Florence yield is low, but they're low. So that means, for example, like carbon, the flow rate is only about 0.001, so it's very low. So that's because when the electron interact with your carbon, so the carbon, I mean the ionized carbon atom, most they prefer to give us the lunar energy by emitting Auger electron. So that's why you usually you cannot see many signals for X-ray. I mean, if you use boron, the Florence yield will be even lower. So that's why usually most of TM they cannot see, most of the EDS cannot see boron. So for higher elements, this rate is high. That's meaning EDS is a very good tool for seeing the heavier elements. Okay, now let's cover another thing. What is the Beam-Structural X-ray? I don't know how to pronounce. Maybe you can say a continuum X-ray. So for this X-ray, it's the background. Sometimes when you see your the EDS spectrum, you will find the signal is very noisy. This means sometimes the background is very high. You need to understand where the background come from and how to reduce the background. So you can see when the electron interact with the column field of the nucleus, there will be substantial momentum changes, and this will emit X-ray. And for this X-ray, I mean it's a continuous, not a characteristic peak. So you can estimate the energy. I mean the number of the photons. I mean for the continuous X-ray, you will see when this energy. I mean the energy is higher, this is lower. So that means for if you want to if the energy is much higher, then the background is lower is much better. Okay, so the next thing I will cover is energy resolution. So many people do not pay attention to this. Actually, this is an important thing. You need to understand that the resolution for EDS is very low, and this is a major limitation. So that's why many peaks, I mean, it's very possible that many peaks overlap with each other in your EDS. So that's why when you do the quantification, you need to pay special attention. The reason that why the overlap is a spatial resolution, the energy resolution is lower. So you can define the energy resolution by the full width at a half maximum of a random electronic pulse generator. So this energy resolution have three factors. One is P. This is related to the electronic pulse generator. The other one is I. This is the intrinsic line width of the detector. So this one can be described as like this. So this one is related to the final factor of the distribution of aggregate counts from the Poisson statistics. And epsilon is the energy to create the electron hole in detector. E is the energy of the aggregate line. And X is the detector leakage. So if we assume that the detector is a perfect one, there is no leakage. The only thing is the intrinsic line width of detector. We can estimate this. So, for example, let's use the manganese K alpha line. The energy location is peak location is 5.9 keV, and the epsilon is for silicon electron hole pair is about 3.8, and the F is 0.1. You can see the energy resolution is about 111 EV. It's very low. If we included the effect from the detector itself, this will be even worse. So that's why the energy resolution is very low. And also you need to know that the energy resolution of your EDS depends on which peak you select. So usually we select the manganese K alpha line. So remember that this energy resolution is very low. Now another thing you want to consider is spatial resolution of the EDS. So the spatial resolution of the EDS is governed by the electron beam and specimen interaction volume. This is a function of the incident beam diameter and the beam spreading. So we can define the spatial resolution using R. It is related to the D, and this D we call is related to the beam, and the beam. Okay, let me where's my screen. So this R can be described using here, and the RMX can be defined here. Is related to the B. B is the beam spreading, and DT is incident beam diameter. So you can calculate this actually. The most important thing here is the beam spreading here. So let's think about the beam spreading. As you can see, the beam spreading diameter is related to the incident electron energy here, and the number of the density of the atom number, and also the foil thickness. You can calculate here. You will see that if the atomic number is larger, larger size, the beam spreading is very large. And if the energy is very high, is higher energy, like 200 keV, this one will be lower. Now this is the B is the beam spreading. Now let's consider the DT is the incident beam diameter. I mean, this is the intrinsic one. This is related to, for example, the DG related to the gun, the electric gun, although the DS is related to the spherical aberration, and the DD, oh sorry, the DD is related to the spread of the diffraction limitation. Anyway, so you do not need to remember the formula.
Hi, Xiaobing. We cannot see the current slide that you're talking about.
Oh, you cannot see my slide?
No, we cannot see the slide that you're currently talking about.
Okay, so I will share again. I don't know why. Now you can see?
Yes, thank you.
Yeah. So I mean, you do not need to remember. I mean, here is a small iris of DD. The DD is related to the diffraction limitation. Actually, so you do not need to remember this formula, but you need to know which factor determine the spatial resolution. So the main thing you need to consider is the beam spreading. This is related to your sample thickness and elements. So you can calculate using this one. And also, I mean, there is some example. For example, if you use, where? So for different elements, the beam spreading is different. So you need to pay attention to this. Then this one is a time constant. This one you will need to use it during your EDS EDS during your acquire EDS. So the time constant usually either time or load for analog processor to evaluate the magnitude of your charge pulse. So the shorter time constant will give you a larger counting rate, but will give a greater error in assignment of a specific energy per pulse. Please remember that, because I mean TM is a little bit different from SEM. For SEM, your sample is very thick, and the sample will generate so many aggregates. So that's why if you use a shorter one, I mean it will contain more error, poor resolution. But for our TM, your sample is very thin. Most of the time, the EDS signal is not enough. So that's why when you do TM, you can choose the shortest time constant to do this. This will be very quick when you do your EDS, and particularly when you do the mapping. So another thing you need to pay attention is the dead time. So the dead time is when the detector is not counting aggregate, but processing the previous phonons. So that means there are too many signals, too many aggregate signals, and the processor, the detector cannot process this quickly. So that's why you have some you have this dead time. So the dead time, we can define this as the output rate. I mean, use this to define this. So the lifetime, I mean, you can also use lifetime and clock time. The lifetime is when the detector is ready to detect the aggregate and not processing any signal. So when you do your experiment, if you saw that the dead time is 50% or 60% is very high, this meaning that the detector is saturated with aggregate and the collection becomes increase inefficient. For this situation, you have to adjust your parameters. You can find the thinner area, or you can also reduce the beam current. And also you can reduce your time constant. So you need to pay attention to this, because if the detector is saturated, I mean, this will contain error when you do, you will include many errors when you, particularly for your quantification, will very inaccurate. But another thing you need to pay attention is if this is very low, for example, it's less than 3%, this means the aggregate signal is not enough. And you need to find some thicker area or increase the beam current. So for our TM, most time you see that this delta time is very low. I mean, the signal is not enough. Okay. Then another thing I will cover is the correction angle. So what is the correction angle? So the right side, I show you a figure. So this is a pole piece, length, and this is a pole piece gap. This is very small, only about for our 300 about 5 millimeter, and for 200 about 4 millimeter. So it's very small. So your EDS detector is here, and you can see the signal only I mean, when the electron interact with your sample, the accurate I mean will at all direction, but your detector can only accept the signal from here in this triangle area. So that's why the collection angle is important. So we can define this. The solid angle is use this formula, and this A is the active area of detector. So usually 30 to 100. So for the old generation detector, this is very small, only about 30. But the new generation detector, this is very large, about 100. This delta we call the delta is angle between the normal of the detector face to a line from detector to the specimen. Normally, this delta is 0. And really S is a distance from the analysis point to the detector face. Now you can see. So the S, if this S is smaller, this solid angle is large. But due to the pole gap is very small, so this S cannot be very small. So that's why the only thing for our TM, if you want to increase the correction angle, the only thing you can do, if the TM, I mean the pole gap is fixed, the only thing you can do is increase the area of detector. And for older generation TM, usually when you do the EDS map, it's very slow, and it will take a very long time. That's because this angle, the solid angle is very small. But for the new generation one, since we increase the, for example, for the old generation TM, the solid angle about 0.3 SR, but for the new generation, about 1. For example, over 200, about 1.7. So it's very large. So that's why you can get a nice signal. And another thing you need to pay attention is this takeoff angle. Takeoff angle is this alpha. So usually this is around 50 degrees. So that's why, for example, when you do EDS, sometimes if you find the signal is not enough, you can tilt your sample around 10 degree, and to make your sample how can I say, like this, then the accurate will go to the detector. Okay, now let's go to the next slide. So now here I will cover some artifacts. Actually, for EDS, there are many artifacts you need to pay attention to. The first one is because when you do the quantification, you need to very clear which is the artifact, which peak is the artifact, which peak is your element. So the first artifact is the silicon escape peak. This is coming from this is due to the signal detection artifact. The detector is not a perfect sync, and the incoming photon with energy E is not transformed into an electron hole pair, but fluorescence silicon K alpha X-ray with 1.74 keV. So now you can see this is the copper escape peak. And another thing is internal fluorescence peak. This is also a signal detection artifact. The incoming photons, fluorescence atom in a dead layer of detector and result in the K alpha peak. Yes. So this is a silicon one. This is this one. And some peak is due to the signal processing artifact. So some peak occur when a counter rate exceeds the electron ability to discriminate all the induced pulse and so-called power pulse up. I mean, this is related to dead time, reduced dead time. You can see some, among this case, some peak, maybe 2 peak either. And for this escape peak, I mean, this is a copper. I mean, reduce. I mean, the copper escape peak reduce this one. So this is some artifact you will see in your EDS spectrum. You need to remove them when you do quantification. And another is system accuracy. So many users, when they do the EDS, they will find even their sample do not contain copper. They will see copper in the EDS. This is normal because copper is everywhere. We call this is a system accuracy. For example, this is your sample. I mean, this is interaction between the electron beam and your sample, and the X-ray will interact with the lens. For example, go through here with a lens, then you will see the signal over copper. I mean, the lens contain iron, also cobalt, also some nickel, also copper. So that's why you will see many signals for the artifact. I mean, it is not contained in your sample. You can see this is an escape peak. I mean, it's a lower. I mean, it's a lower one because the peak from the chromium and interact with the silicon. So the energy loss about 1 point have some energy loss. So you will see this peak. So all of this artifact peak, you need to remove them when you do quantification. Another one is a coherent Bram-Straw lung. I mean, this is some. I mean, most of the time they are continuous. They contribute to the background, but sometimes you will see some separate peak at a low energy rate. So if you see this peak, you need to pay attention. This is not your element. This is related to the artifact of the we call the CB peak. So you can use the formula to calculate this. Okay, now let's go to the next one. So for the EDS, usually the application is very straightforward. You identify the element distribution. For example, this one is element distribution along the boundary, the boundary in a superalloy. You can see some segregation at the rim boundary, and also you can even see the atom at atomic resolution if the EDS your detector is good. So you can see for this one, we can see the vacant layer of the lanthanum within a solid electrolyte. But this one is only the qualitative. We do not do the quantification. Okay, now let's go to use. So for the use, the most important parameter is the cross-sectional differential. You can use a formula to calculate this, but I will point out some important things. For example, this, let's see this. Let's see this E. If this E is the energy loss, if this one is higher, very large, then this cross-sectional differential should be very small. So that's why our use, I mean, high energy loss usually have a smaller cross-section, only a lower signal. So that's why use is sensitive to light elements. And also sometimes you will see in literature, the lower voltage is good for use. That's because if the voltage is lower, this way the speed of the electron is lower, then this will be larger. So that's why sometimes you want to do the use at a low voltage, low kV. And another thing is, okay, I will cover this here. So this is theta. This is theta is a scattering angle between, when your electron interact with your sample, it will be scattered away. This theta is a scattering angle. This is theta E, we call the characteristic angle, and equaling around E divided by 2 E0, this is energy of the electron beam. So I will cover more details for this one later. So okay, so how is this is basically EU spectrum. So it contains zero loss peak. It's very intense, very high peak, and also contains a low loss region containing the plasma peak is also intense. The ionization edges relatively low energy compared background. So also some colors. If the energy higher than 2 kV, usually we cannot see it. It's very low because the higher kV usually have a lower scattering scattering area. So that's why it's lower. So that's why the zero loss peak and low loss peak is very high. Okay, now let's cover one thing: is the energy resolution. Usually, the higher energy resolution can give you more details. So as you can see this one, so this is a peak of iron, I think. So you can see this is the XAS results. This is this is have a monochrome. So if you have a monochrome, you can see more fine details of the peak. And also the only thing, the energy resolution of the TM is determined by the monochrometer. So you can see it also determined by the this one, the half of the intensity of the peak. So usually for our TM about 0.35 eV. But this energy resolution is enough for your conventional analysis. Now I will cover some important thing for use. So one thing is a collection angle. So for a dedicated TM, you can calculate this angle using this schematic. So but you need to pay attention that for your GIF system, your GIF system take the signal on the back focal plane of your projector lens. So take signal from here. And for this angle, usually it's a fixed angle. You can only change your camera lens to. And for the imaging mode, there is also many formulas you can calculate. You can calculate this. Usually, for example, if you do the use in TM mode, it's only about this beta around 100 milligrad. If you use the aperture, it's about 5 milligrad. So I didn't want to cover many details. You can see the detail for how to calculate this. And for STEM mode, you can use in both TM and image diffraction and STEM mode. If you do the diffraction mode and STEM mode, the calculation of this angle is different. You can refer details for how to calculate this. And later on, I would like to say that this is important thing, is how to select the suitable collection angle. For example, this is a characteristic angle for each element. So for most of our elements, the characteristic scattering angle for a colorless electron ranging from 0.2 to 10 millirad. So that's why, but your collection angle should be about 2 or 3 times larger than this one. Because if your collection angle is small, for example, smaller than this theta E, you do not collect all the scattered electrons. That's why your signal will be very bad. So you need to consider a good collection angle when you do your experiment. And sometimes you need to change your camera lens. I mean, as I introduced, in the previous 3 slides, you need to change your camera lens to change the collection angle. So another thing is cutoff angle. So the cutoff angle is the maximum scattered angle of your elements. So usually the cutoff angle for all element electron should be about 200 millirad. So your collection angle cannot be very large. For example, if your sample, the cutoff angle only 25, but your collection angle is 100, then this is not good because you contain many other signal not related to your elements. So it may not good for your quantification. So you need to select the suitable collection angle. Another thing I would like to say is detection efficiency. So actually for the use, the scattered electron is within this area, and the detector can accept about almost all of the electrons. But for EDS, the array is around the 3-dimensional, but the detector can only accept the signal from here. That's why the detection rate for use is very high, but for EDS is very low. Another thing is spatial resolution. So the spatial resolution, I mean, it's depend on your imaging conditions. One thing I want to point out is like this. For example, if your energy loss is very low, if your energy loss, for example, if your energy loss is very low, like 50 kV, and the spatial resolution about 1 nanometer. So the D50 about 1 nanometer, and if the energy loss is 3 kV, the spatial resolution about 0.4. So that's why for some light elements like carbon, like boron, although you can detect the signal of them, but you cannot get use, I mean, 2-dimensional image with atomic resolution because their spatial resolution is low, about 1 nanometer. But for the higher energy loss, you can see this. So, the next one is application of use. So I didn't include the detail, but I want to say that the use can do so many things. It's much more powerful than EDS. It can identify the elements and the concentration. This is a similar function as the EDS. Another thing, it can identify the valence state of the elements, because some elements, like iron, have 2+, 3+. It can identify this. Another thing, the use can determine the bond gap and also the plasma and also some other physics-related phenomena. So use is more powerful. So in the future, we will cover more topic about the application of this. So, okay, that's all on my talk today. So if you have any question, we can discuss. Thank you.